In this video, we're going to talk about the torque that a current loop feels when it's in the presence of a magnetic field. So recall in our previous discussion, we had talked about how the force experienced by a magnetic field, the force on a moving charge experienced by a magnetic field is QV cross B. And then as part of that discussion, we said because the force is always going to be perpendicular to the direction of travel, magnetic fields can't do work, right? And that doesn't mean that there's nothing going on. So specifically, current loops end up feeling a rotational torque as a result of the magnetic fields. Now that is not the same as doing work. So let me clarify a little bit more. Let's say that you have an object like this where the center of mass is in the center, right? And if in this case, if I ended up having a force, one force pushing this way, and then another force going this way, and let's say this is R1 and this is R1 and this is R2, you'll see that if you're just looking at this as a rigid structure that's pinned down and you're looking at the center of mass, these two forces, if they're equal, they'll cancel out, right? But at the same time, even though the center of mass won't move because these forces cancel out, this thing still feels, this particular rectangle here still feels a rotation going this way, right? And that rotation can be described by the torque that it feels. So let's first define torque. So torque, which is a vector, is defined as the radius, the cross product of the radius and the force. So in earlier versions of physics, you might recall that the torque, in terms of if we were just looking at our seesaw example, right? The torque that's felt is the force times the radius from there to the point of rotation. Now, in this case, we're going to more rigorously define it by using the cross product. And the purpose of the cross product is if you take R cross F, that direction is going to give you, so F is going to be this way, R is going to be this way. So R cross F is going to come out of the board. That torque will tell you whether, if in this view, whether the rotation is going this way or if it's going the opposite direction that way. So the vector of the torque is going to tell you what direction the rotation is going, and the cross product will tell you the product of R and F is going to give you the actual amount of the torque. Now, just like what we did with the F equals QV cross B Lorentz force, we can also rewrite this in differential form so that we can look at a differential element of torque. And so if we do that in the case of force, we'll have dt is equal to RT cross dF. And where dF is something that we've found in our Lorentz force equations, we can rewrite in terms of different kinds of current, right? So using this approach, you can for a chunk of current that you've broken down into differential elements, you can find dF, and then from that dF you can then write dt, and then integrate your way to find the total amount of torque. So combined with our previous process for finding dF, let's break this down into a series of steps. So the first step to finding the total amount of torque due to a bunch of currents is use what our previous discussion on the Lorentz force to write out what dF is. So remember, we had several ways of writing dF depending on the kind of current density we have. We can write it as J cross B volume integral, or if we have a sheet current, we can write this as K cross B ds, or if we have just a line current, it can be I dl cross B. So first of all, we find this dF. Next, we find an expression for the R vector. So the vector that represents from the point of rotation, the axis of rotation, to the point where the force is. So first of all, we find RT, which is from the origin to the current location. And then finally, we substitute the 2 into our torque equation to get dt is equal to RT cross dF. And then we integrate, just like we did in our Lorentz force equations, to get the total torque. So before we conclude, I also want to point out, define the magnetic moment, and use that as a way to give you some intuition as to the kind of force that the current loop would get. So over here we have some equations that describe the relationship between the torque and the force, which coupled with the Lorentz force equation gives us a relationship between the current, the magnetic field, and the torque. But I also want you to have just general conceptual intuition as to what's going to happen. So let's first define the magnetic moment. So the magnetic moment is a vector, which is, if this was a magnet, so this is a magnet where we have our north pole and our south pole. The magnetic moment is a vector that runs from north to south, and the length of the vector tells you how strong the magnetic field is. So in the case of if we have a current loop, and we can write this differentially where dm is going to be I ds. And so if I were to try to visualize this, if you have a current going this way, a current loop going like this, then this is your differential element ds. Your magnetic moment is going to be, using the right-hand rule, is going to look like this. The piece of intuition that I want to leave you with is that in general, when you use these equations to calculate the force and the torque that's experienced in the presence of a magnetic field. So let's say you have a constant magnetic field that's going this way. What is going to end up happening is that the force, the torque, is going to be such that the magnetic moment will try to align with the magnetic field. So the magnetic moment now let's take a look at how magnetic fields are defined. A magnetic field is defined as going from north to south, right? So one thing to note is that a magnetic dipole and a magnetic field are defined in the same direction. Contrast that with an electric dipole. An electric dipole is a positive and a negative charge separated by a distance, just like north and south. And in this case, the electric field is defined as going from the positive to the negative current, but the dipole, on the other hand, an electric dipole, is going from negative to positive, so in the opposite direction of the electric field. So to summarize this, what I'm trying to get across is that in the electric field, the dipole direction and the field direction are the same, are opposite. Whereas in the magnetic field case, the definition of the field and the dipole go in the same direction. So in this case, we see that the dipoles are the magnetic dipole gets rotated. It feels a force to get rotated to be aligned with the magnetic field. And so one of the key results is that dipoles, if they are left to rotate freely, can strengthen the magnetic fields. So as a quick summary, we defined torque using this QV cross B in conjunction with the definition of torque. If we plug the force in, that gives us the ability to further see what a given current loop experiences in terms of force and movement as a result of the magnetic field. So we described that magnetic fields can't do work. However, they do cause a wire loop to experience torque. And to calculate the torque, we know that the torque is R cross F. So we can use this Lorentz force equation, plug it into the torque, and then use that to figure out what the total amount of torque that the current loop would experience is. So to break that into steps, first of all, we write down the force due to a differential element of the current, which from our previous discussion of the Lorentz force can be described through the current density or the sheet density or just a current line in a closed loop. That gives the differential force. If we also have an expression for the R vector, we can then put them together to come up with a differential expression for torque, which we then integrate. And then the other concept was in terms of from a hand waving standpoint, just to build some intuition. If you were just given a current and a magnetic field, if you just need to know what direction it was without going through this rigorous calculation, one important piece of intuition is that if you look through the current loop and define a dipole, a magnetic dipole, which goes through the loop, as indicated by this blue arrow, the torque that you feel is that the wire feels is such that it will try to align the magnetic moment with the magnetic fields. And also, because of the way that the magnetic moment and the magnetic fields are defined, in this case, this alignment actually means that magnetic dipoles, if they were left to rotate freely, will orient themselves in a way such that they strengthen the B field.